The key idea of MobileBrick is it is a multi-view RGBD dataset captured using a mobile device, which includes a high precise ground truth shapes for a set of very diverse set of 3D shapes.
Welcome to Talking Papers, the podcast where we talk about papers and let the papers do the talking. We host early career academics and PhD students to share their cutting-edge research in computer vision, machine learning, and everything in between. I'm your host, Itzik Ben Shabbat, a researcher by day and podcaster by night. Let's get started. Hello and welcome to Talking Papers, the podcast where we talk about papers and let the papers do the talking. Today, we will be talking about the paper MobileBrick, Building Lego for 3D Reconstruction on Mobile Devices. This paper was accepted to CVPR 2023, and I'm happy to host the first author of the paper, Kejie Li. Hello, Kejie, and welcome to the podcast. Can you introduce yourself?
Hello. Hello, everyone. This is Kejie. My name is Kejie Li. And so the paper I'm going to talk about today is called MobileBrick, Building Lego for 3D Reconstruction on Mobile Devices. This is a work I did when I was doing my postdoc in Oxford, collaborated with Jia-Wang, Robert from Apple, and Philip Torr and Victor Prisacariu. They are my supervisor at Oxford.
Right. Yeah. So since you already covered the author section of the paper, let's move to the kind of abstract TLDR kind of format in 2-3 sentences. What is this paper about? Yeah, so this paper is a dataset paper, as the title suggested. So it is about building, using Lego to build an RGBD dataset for 3D object reconstruction evaluation, right? So the key challenge in evaluating 3D reconstruction is getting reliable ground truth annotations, right? So there are a few datasets already existing to do this task. One of them is called DTU dataset. I think this is a really famous dataset or a popular one used widely in the research community. And the way they build up this ground truth annotation is they rely on the LiDAR scanning, right? The laser scanning, really high-end laser scanning. They set up the environment in a kind of a lab environment, and they just scan the object from different viewpoints and then filter point cloud eventually to have the final reconstruction. And that is the reference that you can use to evaluate your algorithms, like the RGBD or RGB multi-view reconstruction algorithm. So the problem of building the annotation in this way is that despite the high-end laser is usually really precise, it doesn't really cover the entire object. That's one problem. Because of the self-occlusion of the object, you can't really scan some part of it. So there's a missing surface in this kind of annotation. The other problem is artifact in the reconstruction, in the annotation. Because you still have some, for example, for a certain type of property or surface property, it doesn't really reflect, the proton back to the LiDAR, so it doesn't really read the depth reliably, and some other surface just doesn't really reflect, so you can't really scan it, and some other just have some wrong reading of the depth, so that's why you have some artifacts in this reference, right? So in doing or building up the annotation or ground truth in this way doesn't always give you 100% or exact annotation of the 3D reconstruction. Yeah, right. So basically what you're saying is you're proposing this data set because evaluating reconstructions is really difficult because
other methods, they kind of have to use this sophisticated, very expensive scanners that have issues themselves, right? And what you came up with this kind of neat trick of using Lego bricks, right, to kind of overcome this need, right? Lego bricks, you know the model, right? You have an exact replica, an exact kind of CAD model that you can use to compare to.
Yeah.
And this way, you don't need this whole expensive kind of scanning setup, right?
Yeah, exactly. Like on top of like not everybody can have the capacity to set up the really expensive scanning device or scanning environment, right? So if a bunch of students just want to have something to evaluate their algorithms, then what do you do? Like if you don't have the 3D scanner. So I think Lego, or as I think I'm going to talk about later, Lego is just one example. But I think the key idea in this paper, or the key contribution of this paper, is really introduce a new paradigm to build multi-view dataset for object reconstruction, like how you can build reliable annotation to evaluate your 3D reconstruction algorithm. But I do want to mention the other type of dataset is using, of course, synthetic dataset, right? So if you have the digital model of something, or object of interest, you can always render some RGB images, and in that case, you have the really precise or the exact replica of the model, right? But then in that case, the RGB images are not real. So if you submit your paper using synthetic images, you always have the reviewer tool asking you, okay, does this generalize to real images? And, So if you have submitted any paper, you understand like reviewer tool is a special guy that always give you some trick questions, right? So I think this is really like this data is a really good combination. Like you have the real images, but you also have the really reliable ground truth to evaluate against.
Right. And I guess the point of this reviewer too, right? It's valid, right? Because when we're in this age of, learning and all these kind of huge architectures that allow us to do amazing things, the big question is, well, how does it generalize, right? And if you train on synthetic data, well, that's nice, but most applications use real data. So how big is the domain gap, right? And I think this work is really like right in the place to kind of bridge this gap, right? You have the ground truth and you have the real scans, and you kind of, we're going to talk about it, but you're going to tell us how to kind of align between the two and find like a good way to evaluate reconstructions. And also, I think, all of the methods that kind of try to push themselves, as kind of multi-view or reconstruction kind of methods, they always evaluate on something, right? And it's kind of like, okay, we'll evaluate on what's easiest, right? Okay, so synthetic is easiest, and it's not always the right thing to evaluate. And I think this really kind of fits that gap.
Like in those, a lot of NERV paper, right? You can see they use this, the NERV synthetic dataset, like with the folder. I'm not sure if you have seen that one. Like in those synthetic dataset, you get really, really good no-view synthesis results, right? But does it really translate well to real images? Like if you casually capture an image sequence and you throw it into NERV, I bet it's not going to impress you or impress your friend who doesn't know a lot about computer vision, right? You just say, well, this AI sucks. I guess that's one general answer. So really evaluate your benchmark or evaluate your algorithm on realistic images. I think that is a really important topic for a lot of CV researcher to tackle.
Right. Yeah, I completely agree. But now, okay, so if we kind of have to boil it down to a few bullet points, so what are the main contributions of this paper?
The most important message we want to send out to the community through this paper is this new way of building data set. You have the physical model and then you have the digital model and how you align them.
So instead of using like 3D scanning or synthetic data set to build this data set, right? And I think the other thing is to review how existing algorithms work in such a casual setup. Like, so we evaluate a bunch of different algorithms, right? So it's RGBD or just RGB, or like the backend algorithm, the backbone algorithm is different. Like it is ranged from traditional, those COMAP style to more recently those neural implicit representation like NERF, NEWS, and also we have some like the depth only TSDF fusion, connect fusion, this kind of stuff. So yeah, if you look at the paper, you're going to see like some quite surprising to some people that even you have the depth sensor for this really precise RGB object reconstruction, sometimes the depth resolution is not great enough. It's not good enough to capture those details. So sometimes RGB actually is better than RGBD. So that's one interesting find we have in this paper.
All right, I can't wait to start talking about the details. But before we do, let's talk a little bit about related work. So which papers does anybody need to read before they come and read your paper?
I think it depends on your background, I would like to say, right? So if you are quite new to 3D vision, I think it's not paper, but it's a software package you should use. It's called CodeMap. It's quite a popular library people use to do structure for motion or multi-view stereo, and you can find great amount of resource on how to use this stuff, how to use this software. So by using it, you kind of understand the general pipeline or the traditional pipeline of building, like how to reconstruct the 3D from a bunch of 2D images, right? So there's a classic one. And then more recently, maybe you should read into NERF or NEWS paper. It's called Learning Neural Implicit Surfaces by Volume Rendering for Multi-View Reconstruction. All right. So I think this is really a nice paper on top of NERF. So NERF, I think like everybody basically in computer vision knows what it is at the moment. So it's the neural implicit representation for the 3D scene, so you can do a neural synthesis after you train the nerve to represent some scene properties, for example, density and RGB of the scene. So NEWS change the representation from density to SDF to really force the representation to capture the zero crossing surface to have a better geometry reconstruction. So I think that's one contribution of NEWS. So in terms of the other data sets, I think like DTU, as I mentioned earlier, is a popular one people used to benchmark their 3D reconstruction. So we can have a read on that and see how they're different, how our paper is different from their papers. And what else? I think like, for example, the other paper, the other data set from Meta called Common Objects in 3D, I think it take a really different direction. So they build a really large scale of data set, right? I think I can't remember the exact number of the number of video or number of objects on top of my head. I think, let me just pull up the paper. So they have 19,000 models, whereas we only have more than 100. Like we look really small, right, compared to the common object in 3D. But the annotation level is different. So in their paper, the 3D object reconstruction, like the reconstruction or the ground truth or pseudo ground truth, what they call it, is actually reconstructed by CodeMap. So it's not reliable enough to evaluate against, right? So if you want to evaluate your multi-view reconstruction, of course you want to be better than CodeMap. So of course you can't use CodeMap as the reference. But I'm not saying like Code 3D, like the dataset is useless or anything. It's just like it's doing different stuff, right? It's doing more on objects understanding instead of precise 3D reconstruction evaluation.
Right. So, okay. So if I have to kind of sum up the papers that you mentioned, so we have the DTU dataset, the nerve paper, the newspaper, the CallMap package, and this Co3D
object in 3D.
Yeah, and the Co3D dataset from Meta. All are relevant references, and I'll put them in the episode description so people can access them. All right, but let's talk about this paper now. Okay, so tell us, what did you do here?
All right. So yeah, when building this dataset, I think the first step is buy some Lego bricks, right? Very important step because you need to build Legos, right? So the first step is build some physical models, and then it doesn't really need any computer vision knowledge, right? As you can ask your 60-year-old to do it, they are capable of building Lego bricks. And then actually in our case, we have two sorts of data source for our physical Lego models. The first one, as I just mentioned, we just build it ourselves. And then the other one is we are very lucky that we have a friend who is a huge Lego fan. So he got, I think, several, or I don't know, more than 30 or 50 models, Lego models in his house. So we just borrow the models and do the scanning, do the image capturing ourselves. So we don't actually need to physically, like, step by step to build those models. So that's really lucky for us. So that's the first step, just build a physical one. And then the second one is to build the digital replica of your physical model, right? So that is kind of building the ground truth. So in this step, because Lego actually got a really huge fan base around the world. So we have a lot of software, Lego software that you can use to build your Lego model using, in the software. It's something like Blender. I think the exact name is called, actually we use a few of them. The first one is called MobileBrick. It's a web-based, application that you can just drag your mouse and, build the models. And the good thing about this, website is that not only you can, build a digital replica, one step by one step, you can also import some existing Lego models. For example, we have some, like the friend I just mentioned, he got like those Lego models. It's identical, it's the official Lego model set. So for those model sets, it's really complicated, but we don't actually need to build it because the CAD model is available online, right? So we just need to import it to this MobileBrick website and convert it into PLY file or OBJ file, whatever mesh file you are happy with, to have the ground truth. Yeah, so the first two steps is just building the models. And then the last one is image capturing. So you pull up your iPhone. So in our case, we use iPhone, or you can use any Android phone actually to just go around the object to scan it. Not really scan it, right? Just casually capture this object, go 360 around it. And then the last step is the image alignment. So I think this is the critical step in this data, right? So you have your image capture in one coordinate, and then you have your digital replica of the object in the other coordinate. So in this step, you need to align these two into the same coordinate so you can do evaluation. So in this step, what you do is because we use iPhone, we have some initial camera pose provided by ARKit. So ARKit, like they are able to do camera tracking, but of course it's subject to camera drift and it's just not ideal. So we on top of this initial camera poses given by ARKit, we have some manual annotation first of all. So that is it's just an interface, is a GUI interface. We can click on the mouse, annotate a few 2D key points and also annotate a few 3D key points, like corresponding 3D key points. Then we can run PMP to have the first alignment to
to align the digital model to the camera coordinate, right? So, and that is just the first step. And a second step is a multi-view consistency check. This is also a manual check. So what it does is it projects the aligned digital model to more views in the image sequence to see how aligned it is. And the user or the annotator have the option to refine the camera poses, right? So in these two steps, you have a really good alignment from the digital model to the camera coordinate. However, it doesn't change the ARKit poses, right? If the camera is drift, then these two steps cannot rectify this error. So the last step we did is to run a bundle adjustment on top of these two steps to kind of rectify those camera drift problem. Yeah, so that is how we build a data set. So the first step is build physical and build digital model. And then you capture your physical model using your iPhone or using any smartphone or just any video recording devices you have. And the last step is to align the digital model to your image sequence coordinate.
Yeah, that was a great recap. Let me see that I follow. Okay. So the first thing you do, you assemble the Lego model, right? You go to the store. Well, you didn't go to the store because you had that friend, but you go to the store, you buy a Lego pack, right? Of, I don't know, Harry Potter's Hogwarts castle. You put it, you start assembling it, right? Now you have the physical model sitting on your table. Then, since there's a huge fan base, you have like the actual CAD model provided by Lego. So that's the official model. It's 1-to-1 match to what you just assembled that's sitting on your desk. So now you have something sitting on your desk and something sitting inside your computer, and they kind of match exactly to each other. But now the next step would be to scan the physical one, right? So when I say scan, it's not really scan, right? It's take your phone, you kind of go around the model, right? You get like a multiple views from different angles. And now you have this short sequence of images of this model. And then the big challenge is, well, now you have the video. How do you align it to that 3D model that's sitting in your computer? And this is where you have a lot of kind of very detailed operation and kind of human in the loop kind of annotation scheme, right? Where you get the key points, you get this initial alignment using PNP, right? The key points are human generated. Then you kind of project it, you allow to kind of correct it, right? If it's not too good. And this is like a huge effort, right? I think probably most of the work was done here, right? So how to get this good alignment in such a way that there's an actual physical to digital as close as possible to 100% match.
Yeah, so it's also a quite interesting development there, right? So initially we need to spend, 5 minutes per sequence, to align one digital model to one image sequence. But as we go on, we can refine this process. Like we know how to speed things up, and we also change the interface to more user-friendly, and it's easier to annotate. And so we actually learn a lot, like how to annotate data efficiently along the way. And I think that's quite interesting. It's quite different from like the traditional research paper where you develop a method. This is not about like developing a novel method or have some smart tricks to improve, to get both number in the table, but it's kind of an engineering and fun process, right? Because at the end it's building Lego. So, yeah.
Yeah, but I guess like the main question is and I saw like in the paper, you have that in the results section. So maybe that's a good bridge to start talking about that. So how do you know how good you're aligning, right? What's the accuracy, right? Because even when they manufacture the Lego bricks, there's some level of inaccuracy, right? Some tolerance between every brick, right? They look identical to us, But me as a former mechanical engineer, I know that no two pieces are exactly identical, right? There's some tolerance.
Yeah.
So how good is this alignment process? And I guess what I'm asking is, what is the baseline error that you're working with, right?
Yeah. So to evaluate the quality of our annotation, we basically need to measure two things. The first one is geometry, right? How, like, is the digital replica really 100% to the physical one? So that's geometry evaluation. The second one is the alignment evaluation, right? How good our alignment algorithm can, shift or transform the digital model to the camera coordinate. So in terms of the first one, we borrow a micrometer from the department. So I think the accuracy of that is 10 micrometer, if I remember correctly on top of my head. So we just measure, if we stack up a few Lego bricks, we measure like the deviant from the design or the digital spec. And so that's how we select the threshold in our table. So we use two thresholds when we evaluate the baseline algorithms, right? So we select the first one, the most strict one is 2.5 millimeter, and the more relaxed one is 5 millimeters. So we select these two based on our after we evaluate our annotation quality. For example, if our evaluation quality is like the error threshold is, if we set it to 1 micrometer, then it doesn't really reflect anything, right? It doesn't really reflect the quality of or reflect how good the reconstruction algorithm is, because it's within the Lego brick error. So you can't really tell whether this like 1 micrometer error is from the Lego brick itself or from the reconstruction algorithm.
Right. And so I have to say, 10 micrometers, like, I don't know, most listeners are probably don't have like a notion, but 10 micrometer, that's pretty accurate, right? Like, this is not something that it's noticeable by the naked eye, right? This is something that's very, very small.
But yes, yeah, it's pretty precise, I would say. Because the error source for geometry will be basically the manufacturer error and how hard you press the Lego bricks, right? So if you stack a few Lego bricks, if you don't press it hard enough, then you have some gaps between the bricks.
Right.
So that would be different from the digital replica, because in the digital replica, it assumes these Lego bricks are tightly coupled together. So basically two error source.
Right. So one manufacturing error and one like kind of an assembly error, right?
Yes, exactly. And yeah, so then for the alignment evaluation, we just we run some. So we basically what we did is we have a calibration board lay on the floor, and we capture some calibration sequence. So we place a Lego model in the middle of the calibration board, and we capture the sequence. We run our alignment algorithm and compare that against the calibration result. Right. So that's how we can know like how good because you have no way to tell the exact ground truth of the alignment, right? Because you don't have the thing. So we have to assume the collaboration result is the ground truth, is the pseudo ground truth. So we just compare against our alignment algorithm against that one.
So now you have like this good notion of how accurate your data set and alignment and the manufacturing error and the assembly error, right? So now you know like what's the range of accuracy, and the numbers are in the paper. I don't think they're too important right now. But okay, so what are the benchmarks that once you've got all of this figured out, what are the benchmarks that you ran? Like which methods did you evaluate, and what are the evaluation metrics that you used?
Yeah, so we run several methods, but I think they can be categorized to 3 major types. The first one is the volume fusion type. Right? based on Connect Fusion, like doing TSF fusion using depth map. So the depth maps actually come from the LiDAR sensor of the iPhone 13. So it's not really high resolution that map is getting out of it. And then the second type of algorithm is the traditional multi-view stereo reconstruction. One representative is CodeMap, the widely popular software people use to do 3D reconstruction. And then the third type, it should be 4 categories. The third type is the neural network-based multi-view stereo, so MVSNet. Based on the cost volume, you extract image feature from your input views, and then you do homography wrapping, and you have the cost volume. Then you that's how you get the depth out of the multi-view images. And then the last type of methods we evaluate on our dataset is the most recent neural implicit based method. We use NERV and NEWS, those 2 papers I just mentioned. And I think some interesting result out of this evaluation is that we found out those neural implicit based representation, those NERV and NEWS really stand out from it. Like before we run our algorithm, we all kind of skeptical that does the NEWS or NERV really outperform CodeMap? Because maybe the author really, is it really generalized, right? CodeMap, it has proven that it can work in most of the cases, but does NEWS or NERV can generalize well to those casually captured scenes? So it turns out that it does. NEWS really, it just it's doing great compared to CodeMap or other algorithms. And then the second interesting finding we have is for the method that use depth sensor. So if we always have this bias that if you have the depth sensor, you should use it, right? Because it just gives you quite reliable depth read, and you don't need to recover the depth from multiple images. However, for this detailed object reconstruction, the depth sensor from mobile devices are not high resolution enough. iPhone is great if you want to scan your entire room, right? Because maybe you don't really care about some object details. Your focus is really getting the entire geometry of the room. So yeah, it depends on application, right? So if you want to go for scene level reconstruction, iPhone depth sensor from mobile devices, they are great. It's more efficient, right? So you don't need to run those multi-view reconstruction algorithms. Just run volume fusion to get your 3D reconstruction. But for these tidy objects, this desktop environments, for objects that are maybe you can sit on top of the desk, maybe you should consider RGB images, because usually what we have is we have high resolution RGB images, right? We can easily get 4K images from our mobile phone, but we are still a bit far away from getting 4K depth maps from our mobile phone.
Yeah, I think these are two very interesting finds, right? The first one you talked about, that NERV and NEWS, they're kind of really performing really, really well, because it's sometimes hard to kind of distinguish between the hype and reality, right? Every paper is going to show you the bold numbers, and obviously they're doing good scientific work, but the question of generality always kind of remains. And here you have this kind of independent Dataset and benchmark that kind of says, well, let's see how this works in real life. And it turns out that these 2 methods kind of really shine. And I think this is a really valuable find for both the academic community, but also for industry, right? Probably a lot of companies, people listening to the podcast saying, well, should we start integrating NERVs or NEWS into our pipelines? And we're not sure that it's really going to work because we only saw it on synthetic. And here you can see that it actually can work in reality. And the second find that you talked about, the low resolution NERV integration into the pipeline, and me as a point cloud person, like for me, always use the depth. Depth is amazing. 3D is amazing. But in this particular case, it's not always valuable, right? Because here you have like very fine detail that you want to capture, but your depth map is very low resolution, and it's not, and it will probably give you kind of wrong signals, right? The wrong information or very coarse information that already exists in the RGB high resolution image. So just use that. And I think this is a really valuable find. Okay, so we talked about the baselines and the interesting finds. So let's just kind of now talk about the data set, right? What does it contain, right? Give me the numbers and the subdivision. What is this data set?
So the data set we got, at the end, we have 153 LEGO models in the data set. So each one of these models will have an image sequence for it. And I think the average number of images in one sequence is 60 or 80 frames in one sequence. So that's just kind of the scale of this data set. And within the data set, we have two categories of LEGO models. The first one is the human curated LEGO models, those official models that we borrow from our friend. So those are really, really nice LEGO model, like Ferrari, like you have the replica of some Ferrari and Porsche 911 or the Big Ben building in the UK. So those fancy models. And then we have a large amount of random model sets. So in this random model set, it just these LEGO models, they are not really meaningful. This is not some like really good looking models. They just randomly pick from our blog repository to build it. So but it's about diversity, right? So you don't always want to have some nice model. You want to have some, if we have just some random shape, does it really do well on random shape? And the other purpose of building this large amount of LEGO bricks is this random set is if you want to train your deep network, then you can train on this random set and then test on those evaluation sets. So that's the idea there.
All right. Yeah. So you have the real world set, which is like exact models from Lego, right? Stuff that look like things from the real world or from a cinematic universe or something like that. And then the random set, you procedurally generate random blocks kind of connected to each other, and then you build it in the real world. And that's just about generality, right? You want to see that algorithm is general. So just let me ask you, does the video recording also contain the depth maps?
Oh, yes. So the video recording, we have, of course, the RGB images and also the depth maps from the Apple LiDAR sensor and also, of course, the camera parameters, including extrinsic and intrinsic.
Right.
So,
Okay, so everything you need to kind of do the reconstructions and use for supervision for nerf and use.
That's correct.
And all those kind of methods. Okay, so I think we covered all of the kind of important stuff, but let me talk about conclusions, kind of future work. So how do you see the impact of this paper going forward? And have there been any interesting papers that followed it?
To me, it is quite interesting paper, right? Because it introduced a new way to build a data set. I think it's quite fun. It enable basically everyone, you can build your 3D evaluation data set. You don't have to rely on those 3D scanner. And it is not a compromise as well, right? So we show like it can do as great as those very expensive scanner. And then in terms of the interesting follow-up work, because this is still not published yet, it is going to be appear at CVPR 23. So I'm not sure if anyone has used this dataset yet. I hope people will pick up the dataset soon, but let's see.
Yeah, I hope so too. I mean, to me, one of the reasons that I wanted to have this dataset in the podcast is I think this is like one of those papers that is going to be like a great benchmark. Like every method that's going to say, oh, we beat NERF. Like, I think they should try this benchmark, because it's like, this is the real world, right? It's going to tell you, not in the synthetic world where everything's nice and tight and no problems and no issues, right? This is going to kind of give you a notion of how well this method is going to work in real life. And I think there's a lot of value in that. Yeah. Okay. So now we'll move on to my favorite part of the podcast. What did reviewer 2 say? Please share some insightful comments you got from the review process.
I feel like the review process for this paper is quite good, to be honest, for us. So we didn't have any hilarious question from the reviewer 2, but I think he actually raised a few like valid concern that we thought we might extend the dataset anyway as well. So I think one of the biggest concern is about the texture on the models, which as you can imagine, like Lego model is, you have the plastic kind of texture. It doesn't really reflect how real world object will look, right? So we have very diverse texture on real world objects. I think one way to tackle this problem is really, you can buy the paint material, right? You can paint your Lego models and you give it different texture. It can be matte and it could be like really specular. You can change it, right? So you just randomly apply some paint on top of it. That'd be great. So that's one thing. And then the other thing is kind of linked to the future extension of the dataset. So as I mentioned at the very beginning of this podcast, this is not limited to the Lego, right? So the idea of building a physical one and building a digital one, and then you align them to build a dataset, it can apply to a lot of stuff. Like, for example, the one come immediately on top of my head is the 3D printed object. Like, if you have something you want to reconstruct, you want to evaluate against, you just download the digital model, your CAD model. We have a 3D printer. Now 3D printing is not very expensive. Like, you buy a 3D printer or asking your supervisor to buy for you. And you just print it and you capture an image sequence of it. And now you have the precise ground truth for it. Right? You can easily extend this kind of idea to not just Lego, to 3D printed object. And then for 3D printed object, you can easily apply multiple texture as well. So I think this is really like the future work, or if people want to extend on top of this Lego data set.
Yeah, I can totally relate to that. I mean, I have a lot of working with IKEA assembly, IKEA assemblies, right? So exactly. So even when you assemble a furniture, right, you have a CAD model. Theoretically, you can get or kind of reverse engineer a CAD model of the data set. I know that IKEA recently released a few data sets for the research community to use. But you assemble the furniture in your home. You kind of take a video of that and evaluate the reconstruction on that, and there you can have different textures, right? Because IKEA furniture sometimes come in different colors, different textures, so you can also apply to that. That's a really interesting direction, right? It kind of moves from your tabletop to your room, right? This is much larger items, and it's interesting, I think, to see how well this kind of generalizes to even that, right? Is it like is it size dependent? Probably not, but I don't know. Nobody evaluated, right?
Yeah. It'd be great, like, if you can have some IKEA furniture, like you have the exact model for that. I think back in the days, there's one paper called PEX 3D. They sort of like have this idea, like they go to the IKEA store to capture the chairs, the tables, and they go to the IKEA website to download the CAD model. I don't know where they find the CAD model, and then they just do the alignment. But in that data set is a single image data set, so only annotate one single image to one CAD model. So it doesn't really do the multi-view reconstruction stuff.
Right.
Yeah, but maybe we can
interesting future works
for IKEA. Yeah.
All right. So Kejie, thank you very much for being a part of the podcast. And until next time, let your papers do the talking.
Yeah. Thanks for inviting me. Bye. See you.
Are you interested in 3D and AI? If so, the team at Yume is interested to hear from you. Yume is an Israeli startup dedicated to volumetric video creation. They were voted as the 2022 Best Startup to Work For by the Duns 100. Join their team that works on geometric deep learning research, implicit representations of 3D humans, nerfs, and 3D 4D generative models. Visit yume.com. Thank you for listening. That's it for this episode of Talking Papers. Please subscribe to the podcast feed on your favorite podcast app. All links are available in this episode description and on the Talking Papers website. If you would like to be a guest on the podcast, sponsor it, or just share your thoughts with us, feel free to email talking.papers.podcast@gmail.com. Be sure to tune in every week for the latest episodes. And until then, let your papers do the talking.